Okay, this one is telling us now the central atom for, so several steps dealing with different types of Lewis structures and the electron geometry. So for question, well, part 1 of question 9, okay, it's telling us that xenon difluoride has blank bonding groups of electrons and blank lone pairs of electrons. And the electron geometry of this molecule is blank, and the molecular geometry is blank. Okay? So first, in order to solve this question, we need to first understand what the Lewis structure of xenon difluoride would be. So, xenon is actually a noble gas, so it would be contributing 8 electrons. Fluorine, on the other hand, would be on the 17th column, which is why it would contribute 7 electrons each. So we have 8 plus 7 times 2, which is 8 plus 14. So we have 22 electrons total. So first we're going to draw it out. Okay, we have xenon, all right. And we're going to now put, well, just put it next to each other. Difluoride. Fill out the fluorine's octet rule, because this was sharing only one of its 7. That's how we do 2, 3, 4, 5, 6, 7. Perfect. So right now xenon, though, is sharing 2 of its 8 electrons. So it still needs 6 more electrons. So it would actually be 1, 2, 3, 4. And the reason why I did it like this is because xenon actually has an expanded octet rule. 5, 6. This would be the Lewis structure for xenon difluoride. Fluorine actually already has a formal charge of 0 because, you know, this would be its natural state. Formal charge, 3 lone pairs, 1 bond, which is what it does. Xenon is a little bit more complicated because that one typically doesn't form bonds, but the goal here is that xenon should have 4 lone pairs, okay? But if we're to convert some to bonds, we could actually rewrite this as, because if each lone pair could form 2 bonds, it would be three lone pairs now and 2 bonds, because that one lone pair was able to make 2 bonds. So that would be for xenon, which is exactly what we have here, so that's perfect. So all this has a formal charge of 0, okay? So now it's asking us, it has blank bonding groups of electrons and blank lone pairs. When they ask questions like this, they are actually referring to the central atom, which is actually what they say right there in front of it. So the central atom, how many bonding groups, aka how many bonds it has, that would be 2 bonding groups. And how many lone pairs, as you can see here, 3 lone pairs. So we've answered that part of the question. Now what's the electron geometry? How many total number of groups do we have here? We have 5, okay? So with that being said, with this, the electron geometry, because this will actually be known as sp3d, okay, that's its hybridization. This electron geometry is known as trigonal bipyramidal. Okay, that is the electron geometry. The molecular geometry, on the other hand, okay, funny enough, when you have 2 bonding groups and 3 lone pairs, it would actually be linear. That would be its most stable form, because think of it as the electron lone pairs forming a ring around the xenon and the 2 fluorines sticking out like that on top. So if you look at a plane, this is what it would look like. That ring right here is what I drew as that horizontal line, and this is what we have here for the xenon. And it only works, well, there's different orbitals and different hybridizations, but when you have a trigonal bipyramidal electron geometry where there's only 2 bonding groups and 3 lone pairs, that is what we would get for its molecular geometry shape. We actually check this out with the Vesper theory. So if I went over here and I scroll down, we have 5. Trigonal bipyramidal is indeed the electron geometry. But as you can see here, two bonding groups and 3 lone pairs, you actually can see it is indeed linear. That would be its molecular geometry. So now for this question, they're asking us to determine the molecular geometry. So the second part of this question, determine the molecular geometry at each interior atom in the given molecule below. Okay? So with that being said, we're just going to draw each carbon individually and not really draw what it's bonded to, but just the type of bonds. And the last one is an oxygen. Okay? So it's not actually going to be C4, it's going to be around O. So just as a quick note there. So we're going to draw it out. The first carbon we have is this, double bond and 2 single. For this, we can still say that the electron pair, the amount of bonding groups is still going to be 4, okay? Because it has 4 bonds and 0 lone pair. So the bonding groups we can say it has 4, okay? Well, actually, technically, sorry. This double bond here, that was my mistake. It does just count as just a bonding group, okay? Not 2 bonding groups. So this will actually have 3 bonding groups. This is important because this actually allows us to solve molecular geometry. So this is known as just trigonal planar. And because it has 0 lone pairs, it just has the same name of trigonal planar, okay? That would be this carbon here. The second carbon, actually, funny enough, is the same thing. Also going to be trigonal planar because it has 3 bonding groups total. One of them is a double bond, but the other 2 are just single bonds. The last carbon, funny enough, is now like this. So it's also going to be trigonal planar because it also has now 3 bonding groups. So all of these have had 3 bonding groups, okay? So now we're going to go to the one that's clearly different because now it has lone pairs. The oxygen has 2 bonding groups and 2 lone pairs. So in total, the electron geometry, because that's 4 things bonded to it, that would be tetrahedral. But because it has 2 bonding groups and 2 lone pairs, the molecular geometry known for this is called bent. Okay? So just as a review, the molecular geometry for the first carbon, second, and third carbon should all theoretically be trigonal planar. Because although there are double bonds, those count as just one bonding group when you're referring to its geometry. Okay? So now with that being said, let's see how we did with the whole question. So, exactly 2 bonding groups and 3 lone pairs based on the central atom. So trigonal bipyramidal, which is what we got for electron geometry, and the molecular geometry is indeed linear. So now for the carbons, exactly trigonal planar, which is what we got for the first carbon, okay? Second carbon, also trigonal planar. Third carbon, also trigonal planar. And the molecular geometry around the oxygen, so not C4, but just the oxygen, okay, is bent because it has 2 bonding groups and 2 lone pairs. So this is all correct. So the one distinction I want to stress is that when they refer to bonding groups, even if you have like triple bonds, for example, that still counts as one bonding group, okay? That's why they call it a bonding group, because it could be a single, double, or triple bond that would fall under the same as a bonding group. Let's move on to question number 10.